My name is Mariela Herrera Padilla from the Universidad Autónoma de Ciudad Juárez in Mexico, and the presenting poster is about computational analysis of APT data for trioxide tungsten doped with platinum thin films. The main targets that we want to solve is to perform the evaluation of the mass spectra obtained during the ion evaporation. Given this, atom-probe tomography is used to determine the chemical composition and volumetric distribution in thin films of trioxide tungsten doped with platinum. This analysis is done with the IVES package. The steps for doing this starts with the use of the focused ion beam microscope to help us give the samples a needle shape and so that they can be analyzed by means of the chemical local electron atom probe model LEAP 4000X to determine a sample by atomic probe. Once this is done, the data as obtained by the technique corresponding to a mass spectrum have been evaluated using the IVES 3.8.16 package in the Chemica AP Suite 6.1 software. The analysis involves using the wizard tool to determine a reconstruction of events known as time-of-flight ion evaporation. Once this is done, a calibration has been carried out between the voltage curve that allows the identification of the chemical elements as they are volumetrically distributed in the sample section. Here we have the first image of our results, where we can look at the IVES 3.8.60 package user interface that can be observed the sample reconstruction at the top. Here's the sample reconstruction, and on the bottom we can look at the mass spectrum. On the right side, we can look at the list of analyses performed on the sample, where the first step can be seen that is the mass spectrum analysis. After that, we move towards doing a profile concentration, where we can look which element is shown in the sample in a bigger quantity, and in this case, the target is platinum. On the second image, we can look at the mass spectrum of the thin films after a heat treatment at 600 degrees Celsius, where we can look at different elements that are of interest. The mass spectrum is the first step for the analysis because it allows us to identify the chemical elements and its ions that travel to the detector from the sample according to the atomic mass of each element and its time of flight, which this time of flight is the time it takes the ion to move from the sample to the detector. Every ion that are under the same electric field which allows the acceleration of these ions to be plucked from the sample to the detector. Given this, it is possible to identify the ions of each element because depending of the charge of each one, the atomic mass changes. This can be shown in the image as we can look at the elements of platinum with charge 1, and then here we can look at the platinum at charge 2, and also we can look at the trioxide tungsten with charge 1, and then moving to the left we can look at it with charge 2, as well as WO3 and dioxide tungsten. Given these results, the analysis carried out by means of the atom-probe tomography instruments and the use of the IVES 3.8.16 package have allowed to locate the volumetric chemical distribution, which implies it was possible to locate regions of interest and attributes in the sample where the nearest neighbor distribution stands out, as well as heat maps based on the platinum concentration profile with the objective of identifying agglomerations. In turn, the radial distribution functions of the different samples were obtained taking platinum as the center, which represent the concentration as a function of the radial distance of a set of ions, in this case argon, trioxide tungsten, W2O5, and dioxide tungsten. Thank you for your attention.